Welcome to a video on circles and ellipses, which come from conic sections. So imagine if you had a cone and you were to cut it by a two-dimensional plane parallel to the base of the cone. That cross section will be created here in the shape of a circle. Now, if the two-dimensional plane cuts the cone at an angle that is not parallel to the base, and the two-dimensional plane doesn't go through the base at all, then the cross section will be an ellipse, or another word for ellipse is an oval. So we're going to start with the circle. The definition of a circle is a set of all points that are the same distance from the center. So here we have a center, which I'm going to call letters H and K. And here's going to be a random point that's going to be on the circle. So imagine I were to measure this distance and I kept this distance always the same to all of these blue points here. So that creates a circular shape. And I have another definition for you here. Locus is a set of all points whose coordinates satisfy a given equation or a condition. So we need to come up with an actual equation of a circle based on the definition that the distance from the center is always the same for any general point x, y. So after seeing the circle, let's take a look at what you have learned about distances between 2 points. So we know that distance is a square root of the difference in x values squared plus the differences in y values squared. Now, the distance here for a circle, we're going to use r to represent the radius from center to any point on the circle itself. And so if we're actually going to use r for the distance, and then h and k for one of the x and y values here, we're going to have this equation. And if you square both sides, we're going to get the equation of a circle that is centered wherever you wish at center hk. Now, another way to develop the equation for the circle is actually to think about the Pythagorean theorem. A squared plus b squared equals c squared. Now, Pythagorean theorem only works for right triangles, so I'd like you to imagine wherever the point is from the center, you could always draw a triangle. So the horizontal distance here would be the differences between this x and this h. So the difference between these is the size of this horizontal line. Same thing with the vertical line. The differences between y and k will be this size. And so if you were to put for one side of the triangle x minus h squared, the other side would be y minus k squared. And then the hypotenuse of this right angle triangle is the radius. And so you get exactly the same equation as you would have gotten from the distance. Now, in terms of notation, when we're talking about distance, it's usually very beneficial to talk about between which 2 points. So you could say distance, and as a subscript, you could put down C and CP. So C is the center, P is this point. Or if you've already seen vectors, you could have said that it's vector from C to P. So this is a vector symbol over here. But then because we're interested in just the size of the vector, you would put these absolute values or magnitude symbols on the vector to indicate it's just the size from C to P, which is the same as the distance. So I'll be using that in the video. So I just want to remind you or introduce you to this new notation. All right, so now we're going to talk about this quick summary. So the key concept for the equation of a circle with any center hk with a radius of r, this is the formula. I showed you where it comes from. What we're going to do right now is actually have an equation that's given to us, and we're going to sketch the circle. There's a hint here that we have to complete the square because the way this is written is not written in this format. So in order to get it to look like this, we want x to appear only in one spot and y to appear in one spot. Right now we have y in 2 places and x is in 2 places. So this is not what we want right now. So we're going to complete the square. So in order to complete the square, I'm going to reorganize it a little bit. I will keep the 2x terms together, and I'll put the y squared first with the y afterwards. And I have space left over here to complete the square. So as you recall, you're going to take half of this term here, the coefficient 4, half of it in squared, you get the number 4. You're going to add this 4 and subtract the 4 so that you're not changing the question. So the original thing is the same thing as adding 4 and subtracting 4 is like adding a 0 here. Now, because we have an actual equation on an expression, instead of saying add 4, subtract 4, we can also say add 4 to both sides because this is still equivalent. So imagine the minus 4 just got moved to this other side, became plus 4. Now, I do want to quickly remind you why do we take this coefficient, half of it in squared? Why does that truly complete the square? So imagine this blue, x squared plus 4x, is represented by this rectangular shape. We have x squared block, so that's an actual square here. And then we have another piece here that's 4x in size of area. So what we're going to do is we're going to take this yellow block and cut it in half, right? It's 4 divided by 2, so cut it in half. And we're going to move this block that's shaded in red to this side. So this shape that right now is a rectangle will be more resembling a square. That's why we call it complete the square. So notice that this block over here is no longer shaded, it's down here. So this original one was 4x. That means because we cut it in half, that means this area here and this area here is now 2x each. Let's get rid of the original. So now we have a shape that's resembling very much like a square, but it's missing this corner. So the question is, what is the area of this corner? So we need to figure out what this purple area is. Now, in order to do that, we're just going to look at the dimensions of each of these shapes. So this is a square with area x squared. That means this is a length of x and width of x. Do the same thing for these two rectangles. They're identical. So because the area is 2x, that means this must be the 2 and this must be the x. Why this must be the x? Because it's the same size as this one vertically here. All right, so on this side here, we have x, and this would be 2 as well. So that means that this little tiny square over here will be size 2 by 2. And 2 by 2 has an area of 4. And that's why we had to add the 4 over here to create a perfect square. So this expression in yellow, that is a trinomial, can be recorded in a way where x will appear in one spot. So right now I have x plus 2 twice, but because it is identical, eventually I'll make it x plus 2 with a square. So I just want to quickly explain where this x plus 2 comes from. Because this is now a perfect square, you could look at this whole shape here and look at the dimensions here. Well, this length is x plus 2, so this is the x plus 2 length. This one's supposed to be width. Well, x plus 2 is also width. Because it is a perfect square, that's why we call it complete the square, this could be recorded with just x plus 2 with a square on it. So we got an expression here that had x's in two positions, and by completing the square, we got x to appear only in one spot, which is going to now resemble what the equation of a circle is supposed to be, so that we can actually locate what the center is. From the original equation, we cannot tell that. So we're going to repeat that on the y's. So we're going to take this coefficient here, cut it in half and square it to find the special number 9. We're going to add or subtract 9 here, or as I said before, because it's an equation with left side and right side, we're going to just add 9 to both sides. And then when you look at these three terms over here and you complete the square, you'll have y minus 3 length and width, or you could just record it once with a square. So now that x and y appears only in one spot, this equation actually matches the equation of a circle that we've developed. And so the center here would be using the formula here. In the formula, you'll notice how it says x minus h, but the center here is positive h. So you have to actually switch the sign here. So for us, if you take a look over here, it says x plus 2. So that means the h actually is negative 2. And then y minus 3. So because that's negative, then we actually switch the sign again. K here will be positive 3. In terms of the radius, on the other side, we have r squared. Well, for us, in this position is 16. So set the equation up by saying r squared is equal to 16, and then you can square root both sides to get your radius of 4. Now we just need to practice drawing this. So start by plotting the center. So 2 to the left and 3 up. And then from the center, just count up 1, 2, 3, 4 units. Count down 4 units to the right and to the left 4 units. And then you can just draw the circle by doing the quarter of a circle this way, because I have trouble drawing a perfect circle. So you can just separate little pieces like that. And this is good enough as a sketch. In the second part of the video, I'm going to talk about the ovals or the ellipse. So first of all, I have two definitions here that I should talk about, and then I'll read this main definition of an ellipse. So we've heard of vertex for parabola. So we have vertex also for an ellipse, and we have something that's called a co-vertex as well. So a vertex is going to be called the extreme point on a conic section. So the oval or ellipse is the conic section, and the far points over here that are in purple, those are the vertices. Now we can also call these 2 points co-vertices. They're closer together, so we add the word co in front of that. Then there is the term focus. So focus point is used to construct and define a conic section at which rays reflected from the curve converge, and the plural of the focus point is foci or foci. Both ways are okay to pronounce. So if you were to imagine light rays coming from a straight line over here, a source of light that emits rays, and as they come into an ellipse, they would be reflected right into this focal point. So this type of technology is actually used for in medicine as well, when they're trying to maybe break up some sort of kidney stone, and they could focus rays at one specific point. Now, how is an ellipse created? So let's read the definition here. An ellipse is a set of all points for which the sum of distances from 2 fixed points, the foci, is constant. So I will demonstrate that in a bit. And just as a note, because we're going to study several conic sections, in the case of ellipse, there will be 2 foci and 2 directrices. Can't pronounce that. So this directrix over here, we're not going to use it very much for an ellipse, so I won't define it right now. We'll use it in the next video for parabolas. So in order to continue, I'm going to define a few more terms here. We have vertex, we have the focus point. Then you need to also know that this longer length from one extreme point to the other extreme point, we call it the major axis. And the length of it is going to be 2a. So if the size from the center to the edge would be size a, as shown over here, then obviously that would be 2a, because you're going from center to this edge and from center to that edge. Then we have also a minor axis, which will be size 2b. So if this size from the center to this outer edge is size b, because we're going both directions, is size 2b. Now, before I move on, I did mention a bit about the medical use of ellipses. Let's read this one as well. Ellipses have special reflective properties. Energy waves emanating from one focus point will bounce off the ellipse and travel to the other focus point. So this is a little bit different than the discussion with the directrix. There are such things as whispering galleries. They are elliptical domes where any sound waves produced at one focus can be heard at the other focus, and nowhere in between. The statuary hall in the U.S. Capitol building is elliptical. John Quincy Adams, while a member of the House of Representatives, discovered this acoustical phenomenon. He situated his desk at a focal point of an elliptical ceiling and could easily hear conversations being held at the opposing party's leader's desk located near the other focal point. So a little bit of history, hopefully that's correct. I found this somewhere, found that interesting. And then I've already mentioned this, non-surgical treatment for kidney stone, so you don't have to cut up a person. They try to break up a stone. It's called extracorporeal shockwave lithotripsy. It uses the same reflection property of the ellipse to break up the stones without damaging any tissue around them. A patient is positioned in an elliptical chamber so that the kidney stone is at one of the focus points, and high energy sound waves are created at the other focus. The sound waves reflect off the wall of the chamber and converge to break up the kidney stone. All right, so how do we proceed with this? So I'm going to actually talk about now this sum of two distances. Like, what does that mean? How do you actually create this ellipse? So I have here a picture, and I will put a random point A on the ellipse. And here we have the two focal points with these two red dots. So this distance D1 plus this distance D2, because it says sum of two distances, is going to be the same as if I put another random point on the ellipse. So let's say I had point B here. So this distance D3 added with this distance D4, the total sum is the same thing as the sum of the red ones. And of course, if I would put up a random point right at this edge over here, then the sum of the blue ones, D5 and D6, will also add up to the same thing as the red add up to and the green lines add up to. So this is the relationship that this is saying, that the ellipse is created from these two focal points. So now I'm going to discuss with you what do they all add up to. So it's always the same distance, no matter what point is on the ellipse. What do they add up to? So I'm going to move this size D6 back to where it was. Notice how it's from the focal point to the edge or the vertex of the ellipse. If I were to move it to the other side, I will have it over here, which is also from the focal point to the vertex. Now, if you were to add D5 plus D6, you'll notice how it goes from the vertex to the vertex. We already talked about that that's the size of a major axis, which is going to be doubling the A, right? So if you were to size up this A from center to the vertex, well, because there's going to one side and to the other side, so that's double A. And that's true for the blue ones added up, the green ones added up, and the red ones always going to be adding up to this 2A. Next thing I'm going to do is I will concentrate on the point B. Point B right now is going to be right above the center. So I'll erase everything else. And we're going to develop another relationship between the A, the B, and the C right now. Let's see what it's going to be. So first of all, from the center to the focal point is size C, as you could see over here. And from the center up to the co-vertex is size B. All right, so let's talk about what is this hypotenuse of this right triangle going to have to be. Well, because B here is located right above the center, and this triangle over here, this big one here, is going to be an isosceles triangle. So these two things are equal to each other, so let's call it 2D. And we know that all of these add up to 2A, so if you were to solve this equation, you'll know that D has to be actually the size A as well. So what does that give us? Because it's a right angle triangle, we can actually create a Pythagorean theorem, which looks a little weird because we usually have C on this side. So we have two sides of a triangle, so B squared plus C squared is equal to this side, D, which we also know it's a size A as well here, so A squared. Note, it is better not to relabel A and C. So just because you want C to be the hypotenuse instead of A in the Pythagorean theorem, please don't say that this is size C from the center to the edge of the vertex, and then size A is from the center to the focal point, just to make it match to your usual Pythagorean theorem. The reason being is that later on, when we study the equations of hyperbolas, the equations of ellipse and hyperbolas will have a lot of similarity, but also some differences. Namely, the similarity would be that the 2A for hyperbolas and for ellipses will always be connecting the vertices. The difference between the two things will be that the A will always be biggest number for ellipses. That's not going to be the case for hyperbolas. So I'll come back to revisit this later on. Right now, this means nothing to you because you don't know what a hyperbola even is. And final note I want to say, so here I have the summary that a squared is always going to be bigger than the b squared, and because it's always bigger, we can think about it as always going to be the hypotenuse in this relationship. Another thing I want to point out is that if I had this size from center to the focal point, size c, from center to the edge of the circle, or just above the edge or just below the edge, size b, to the co-vertex, then we already know that this is going to be size a. Now, I just want to discuss that my picture here is a little bit warped because it's supposed to be exactly the same length as this yellow, right? We said that size a is from the center to the very, very edge, or to the vertex of the ellipse. Well, this size and this size is supposed to be the same size, and right now it looks like it's shorter for me. So these vertices, or sorry, this focal point should be closer to the actual vertex. But I just drew it this way just because it's easier to label things when things are not scrunched in together. Now, what is left? We need to talk about the locus for the ellipse. Remember, the locus is a set of all points whose coordinates satisfy a given equation or a condition. So the condition is provided here. We want to transfer this condition to an actual equation using x's and y's for a random point on the ellipse. Remember that the random point on the ellipse here, an ellipse is defined to be a set of points. So this is one of the points that I drew here, for which the sum of distances from two fixed points, the foci or foci, is constant. So this d1 plus d2 is going to be always equivalent to 2a, where a is from the center to the outer vertex. So we're going to create an equation, first of all, by making sure that our ellipse is centered at the origin. Otherwise, it's going to get too complicated. It's already a bit complicated, so we don't want to overcomplicate it, things at this point. So we're going to develop this equation using the origin as the center. So if this was the center, 0, 0, then that means one of the focal points is going to be at c, comma 0, because it's just c to one side, or negative c to the left of the origin. And then the point up here, that could be moved all the way around this black ellipse here. This point A, we'll just keep it as general x and y. Please recall the distance equation. We've talked about it before. And what I'm going to use is the notation that I've discussed previously, is the size of a vector. So we have point A to point F1, so focal point here. And we're going to think of this vector just the size of it, or the distance between those 2 points. Okay, so this notation is something that I'm going to be using. And if you look at our first definition, we did say that d1 plus d2 is always going to be 2a. So while d1 is distance between f1 and a, and then d2 is distance between f2 and a. So then we're going to create the following statement using this distance formula. So plugging in each of the coordinates, you can see that it will be x subtract negative c. So double negative there makes this into a plus. And then y minus 0. So that's this y minus that 0. Then distance from this one to the second one over here, same idea, x minus c plus y minus 0. All of these terms will be squared. All right. So then you may have seen this in your studies, or you may not have seen this. To solve an equation that has roots, or I shouldn't say solve, just reorganize this equation so that the roots disappear, you would have to isolate one of the square roots. So I'm just going to move this one to this side by making it negative, or subtracting it from both sides. And I'm going to square both sides as a whole. So this whole side gets squared and this whole side gets squared. So in order to continue simplifying this, we know that squaring a square root will make the square root disappear. So then we just have the inner part on this side. On this side over here, we have to think about that this whole bracket is multiplied by itself because it says a square here. That means we're going to have to multiply 2a by 2a, which is 4a squared. Then we need to multiply this one by that term twice because it's like if you studied FOIL, so first terms, outer terms, inner terms, and last terms all multiplied. So you'll know that the O and the I will be actually identical to each other. So we'll have negative 2a of this square root. I was lazy to record the actual part on the inside. It's this part here. And then negative 2a of the same. And then plus, because this term times itself, negative times a negative will be positive. And then this term times itself will be a square with the square root, which will simplify to have no square root. All right. So next thing I'm doing is actually expanding a little bit more each of these binomial with a square. So again, using FOILs, so x times x would be x squared, x times c twice because we have to do the inner and then the outer, that will be 2xc, and then c times itself, so c squared, copy down y squared. This 4a squared is copied down. These two are identical terms. We can collect them together and say negative 4a of those square roots. And then this square root with that square will undo each other, but then you want to clean this inner part up, meaning we're going to expand this or FOIL this again. So this x squared, so x times x will be x squared, x times negative c twice because it's the outer and the inner together, so negative 2xc. And then negative c times c will be positive c squared, and then copy y squared. By the way, what I'm doing right now, you wouldn't have to repeat this. This is just a development of the equation. Once you understand it, you'll just use it. So you would not have to recreate this for me later in any of your assignments. Now let's clean things up. Notice how both sides have x squared, c squared, and y squared. So we can just subtract all three of those quantities from both sides. And what I will do is take this square root, because our goal is to get rid of the square root one more time. We're developing here an equation for an ellipse, and we want the equation to be as simple looking as possible. So we'll move this to this other side again, isolating that square root so we can square both sides like we did on line here with the red, okay? And because we want to isolate it, we want this term to this side here. So what happened there? Why is there 2? Oh, right. So this is 2xc, and this is negative 2xc. So when you move this to the other side, there will be negative 4xc total here. Now notice how every term here has a 4, so we can divide everything by a 4, and at the same time also expand what's inside of that square root. So the square root came from this side, so it was the square root over here. So we will expand this binomial with a square, so x squared. Then we'll have x multiplied by negative c twice, so this is this term. And negative c times negative c is the positive c squared, and then we still have y squared over here. All right, so I'm not going to divide by a here because it's monomial, it's multiplied. I'll square both sides as it stands right now. And please remember the rules for squaring things. If it's a monomial term, so it's only one term, then you can multiply every factor by itself when you're squaring it. But if it's a binomial or any more than one term, so here we have binomial, you cannot just square this and square that. You have to actually expand it by doing the FOIL. All right, so let's take a look how it's going to look. So this a squared, here it is. Square of the square root makes the square root disappear. And then here we're doing the FOIL, and the OI of FOIL I'm doing together here. So a squared times a squared, here it is. This times that twice, right? So that's this term here. And then negative xc times itself will be positive x squared c squared. Then we can just expand a squared into each of the brackets. So you can see a squared here, everywhere. We got an a squared. And then we can also look at, well, this term repeats, so we can get rid of that. And we can move this term to the other side. Okay, so here we have the following representation. So this a squared, a to the 4 stayed, this stayed here. This came from this other side, this stayed, and this stayed, right? So let's move on. Next, we have this relationship up here about the relationship between A, B, and C. So we know that c squared could be rewritten as a squared minus b squared, and that's what I did over here. So both for this c and for this c. So I'm looking to develop a formula that just uses the a's and b's without using the distance to the focal points, okay? Because the focal point is not on the ellipse itself, but the size a goes from the center to the ellipse, and size b is from the center to the ellipse, right? So I would like to have an equation as simple as possible. So when we do that and expand this x squared in here and expand or multiply in negative a squared into that, this is what you would have. Then again, you'll notice how we can collect like terms. So this a to the 4 minus a to the 4 will subtract together. Then on this side, we have x squared, a squared, and on this side is also a squared, x squared. Both of them are the same just because they're different order, doesn't matter. We can subtract that from both sides. And then we have this result in the end. Now what we're going to do is put all the x's and y's on one side, okay? And to make this equation even simpler, what we're going to do is divide every term by a squared b squared. Watch what happens. This side becomes just 1, and here b's will divide out, and on this side, or this term, a's will divide out. So here is an equation of an ellipse that is centered specifically at the origin, and A is the longest. So the ellipse that I started with is a horizontal ellipse, so it's more stretched out horizontally, but this could have been stretched out vertically as well. In that situation, then the A would have been appearing where B is. Okay, so A must be the biggest or on the major axis. So that means if you see the biggest term underneath the X, that means it's going to be more horizontal ellipse than vertical. All right, so here is the summary of all of the equations. Notice how I have above here, ellipses centered at the origin first. So if A is the biggest and it appears underneath the X, then it's going to be a horizontal ellipse. If the A, the biggest number that you see, will be underneath the Y, then it's going to be a vertical ellipse. Then we have the position of the foci or foci points. Focal points. So here we have those two coordinates to take a look at. The length of the major axis is always going to be 2a, and length of the minor will always be 2b. We've mentioned that before. What I have here also is what if the ellipse was shifted to another center? It doesn't have to be at the origin. So the only thing that changes in the equation is instead of having just x squared here, you will have x minus h with a square and then y minus k with a square, very similar to the equation of a circle. All right, and then you can see the adjustment for the foci as well. All right, so this picture right here has a summary of what we need. So this interesting Pythagorean theorem, if you were to isolate c squared, you'll see that it's going to be a minus b squared, or a squared minus b squared instead of a plus sign, just because we've talked about the reason why it does that. So you're going to just make sure that you remember that. And then a is always bigger than b here. So let's take a look at how to do a question that you would be required to know how. So the development, you don't have to repeat for me, but you will be required to do something like this. So you need to show all the information, meaning all of these pieces of information on a sketch, and you're given this equation, and notice again that x appears in 2 spots and y appears in 2 spots. So we need to complete the square so that all of our equations, whether it's centered at the origin or not at the origin, x and y appear only in one specific spot in the equation. So just like before, we're going to complete the square. So I'm going to reorganize both of the x's together and both of the y's together. So just change the order a little bit. We're going to factor out the coefficient of the x squared in order to complete the square. So 32 divided by 16 is 2 over here, and then negative 8 divided by 4 is negative 2 on the y. Then we're going to take half of this coefficient, which is 2. Half of 2 is 1. Squaring it will give us positive 1. And we're going to add and subtract it over here. Don't do it on the other side yet because we have a coefficient in front here. So when we pull this negative 1 outside of this bracket, it will have to get multiplied by 16, and then we'll pull it to the other side after. Same thing on this side, it's just negative, but when you square something that's negative will still be positive 1, and then subtract 1 to make sure that you're not changing the question. So then after we complete the square, these three terms, this trinomial is a perfect square, which will be x plus 1 with a square. So if you were to expand this, you should get these three terms back. This negative 1 times the 16 coefficient would be negative 16 here. And these right here, this trinomial over here will give us y minus 1 with a square. And this negative 1 will have to get multiplied by this coefficient, negative 4. So now x does appear in one spot and y appears in one spot. But we want to get it to look like that we have a single 1 on this side and only two other terms on the, this other side here, with one term with an x, the other with a y. So we do not want these terms to hang around here yet. So we're going to add 16 and add 4 to both sides to get 64. And now I want this 64 to become a 1. So I'm going to divide every single term by 64. And so now this is a 1, and so we can see underneath the y is a bigger number. That means this ellipse is going to be more vertical. So let's take a look. So as soon as you have this term with 1, and you see that there's a plus sign, by the way, a hyperbola will be very similar to this, but it will not have a plus sign between the terms. It might have a negative, okay? So we know it's an ellipse because it has a plus sign. We have a 1 here. So you're looking at the denominators, whichever one's the bigger one, make that to be your x squared or a squared, and then a would then have to be just 4, and then the smaller one would be b squared, so that means b is 2. So the bigger value is under the y, so the major axis is going to be vertical. So using this relationship of the Pythagorean theorem, which is with the hypotenuse of a squared, right, because there's a minus sign here, we need to find that the size of c, because c is going to tell us where the foci are going to be located. And so a squared minus b squared will be 16 minus 4, which is 12. And when you do the square root, there's a positive and negative because it goes to one side and the other side, right? There's two of them. And approximately it's 3.5 units. So then what you want to do is state what the center is, but also plot it. So I want everyone to make sure that you label everything, not just plot it, because it does say show all the information and the sketch. So in order to find the vertices, remember vertices are the ones that are farther away from the center. Well, we know that the A is size 4, so you go up by 4 units and down by 4 units, and you can state the vertices themselves. Then remember that there's co-vertices, that ones that are closer to the center, and we're using this B here, so size 2 from the center and size 2 from that center right there, and label the points as well. Then draw the ellipse using, you know, the quarter curves over here, and then we can locate where the focal points are. Remember, they're going to be always near the vertices, not near the co-vertices. They're right there. And in order to find what that point coordinate is, you're going to use the formulas provided here. So because it's a vertical ellipse, we're using this one. So that means the value of the center, -1, stays the same because they're all aligned on the same x value of -1. But then the y value would be whatever the center point is, either plus the c that you found over here or minus, depending whether you're going up or down. And then finally, because you're supposed to state all the information, you should say that the major axis is 2a, which for us is size 8, all the way from this blue dot to that one over here. And the minor axis, which would be 2b, so from the green dot to that green dot, the size is 4.